The International Council on Systems Engineering, INCOSE, develops and disseminates the transdisciplinary principles and practices that enable the realization of successful systems.
System engineering is one of the few disciplines which are transdisciplinary or multidisciplinary, that brings all the different specialities together, that allows people to look from different viewpoints into the issues that we have before us. Whether that's building automobiles, whether that's developing rockets, the combination of those many different disciplines that makes the difference.
INCOSE connects systems engineering professionals with educational networking and career advancement opportunities in the interest of developing the global community of systems engineers and systems approaches to problems.
If you exist within INCOSE, what you have is the ability to connect beyond your corporate bounds, beyond your geographic bounds, beyond your application domain bounds. Learn, if you're an aerospace engineer, learn how automotive tackles it. Learn how biomedical tackles it. What can you take from their practice back to yours? What can you offer to them?
We focus on producing state-of-the-art work products, particularly standards like ISO 15288, that support and enhance the systems engineering visibility and use in the world.
INCOSE can only do anything but support you in building your career in systems. So you will actually meet people who work for different employers, and so you'll get some insight on what opportunities are out there. You also get the access to training material. You can actually use some of the members as mentors. You can bounce ideas off, so it's a number of formal and informal activities.
INCOSE growth is significant. Since forming in 1990, it includes a membership that represents a broad spectrum from student to senior practitioner, from technical engineer to program and corporate management, from science and engineering to business development.
Volunteering for INCOSE allows you to explore different avenues of where you can go in your own career, where you can help in the future of system engineering. And then also it just gives you a community and a network that are interested in similar things that can help guide you and mentor you in your own career. So I think that is one of the true values of volunteering.
Members work together to advance their technical knowledge, exchange ideas with colleagues, and collaborate to advance systems engineering.
You sometimes miss out on the opportunity to mix with like-minded people. If you're based in Europe, you can go to the UK, or you can go to Germany, or if you're in the US, it's just because it's a larger country, there's a lot more things happening that you could attend. So the value I really get out of it is just the network I've built and the relationships that I've built over time.
INCOSE's vision is for a better world through a systems approach, with 18,000 plus members, 75 plus chapters, and 55 plus working groups, supported by 120 plus CAB members. We are a strong council in systems engineering. INCOSE's mission is to address complex societal and technical challenges, enabling, promoting, and advancing systems engineering and systems approaches.
When I pick up the Vision 2025 of INCOSE, I get excited and I get energized because it talks about applying the tools of systems engineering to non-traditional areas outside the military aerospace sector, outside manufacturing, things like public policy, socio-technical systems, lots of areas where systems engineering can bring value.
INCOSE's vision encompasses improving the professional status of all persons engaged in the practice of systems engineering. We aim to encourage governmental and industrial support for research and educational programs that will improve the systems engineering process and its practice.
Boa noite, good evening, good morning, good afternoon, wherever you are. Welcome to another INCOSE Brazil live session. My name is Fábio Silva. I'm one of the directors of INCOSE Brazil. I will do a quick introduction in Portuguese, and I will be back to English and introduce our guests for today. Boa noite a todos. Mais INCOSE Brasil Live Sessions. Hoje nós teremos o Wheatcraft, um profissional muito experiente na área de requisitos. Ele vai abordar um pouco de desafios e oportunidades na área de desenvolvimento, de identificação de necessidades e gerenciamento de requisitos. Espero que vocês tenham uma noite proveitosa. A sessão será toda em inglês, mas vamos disponibilizar depois no YouTube as legendas em inglês e talvez em português também. Tá ok? Temos um formulário de feedback no final para coletar qualquer sugestões e avaliações. Então fiquem à vontade. Espero que vocês gostem da sessão de hoje. Okay, back to English. Again, my name is Fabio Silva. I'm one of the directors of Incosi Brazil. And we're here today with Lou Wheatcraft. It's our special guest for today. So Lou is a senior consultant with over 50 years of experience in systems engineering. He's an expert professional with focus on needs, requirements definition and management, as well as verification and validation. He's a former chair and current co-chair of the Incosi Requirements Working Group. He has taught over 200 requirements seminars over the last 20 years and supported clients from many industries. He has a bachelor's degree in electrical engineering from Oklahoma State University, master's degree in computer information systems from University of Houston, master's degree in environmental management from University of Houston, and he completed the coursework for master's degrees in studies of the future from University of Houston. A lot of diverse information and that he learned. So I hope we get a lot of out of it from the session today. Lou will do a bit of presentation today, and we'll have a discussion after the presentation. So if you have any comments or questions, just please feel free to leave at the chat box. So we're gonna go through all of them and answer and discuss. We have also a feedback form that we'll share with you on the chat box at the end of the presentation, at the end of the session. And please give us your valuable feedback and suggestions for us to improve and for us to have more ideas for future events. So with that, I will just put Lou here with us. So Lou, welcome to our Incosi Brazil live session. Thanks for your time today, and I hope you enjoy as well this session and the questions and comments from our community.
Well, thank you very much. I'll go to the presentation screen now. Let me know when you can see it.
Now presentation is on.
Okay, so thank you for having me. We're going to talk about challenges of needs and requirements, definition and management of complex systems. You just went through my bio. It's in the copy of slides, which I made available. So you should be able to get a copy of the slide deck after the presentation. So in the introduction to Incosi, they mentioned of 55 different working groups. The largest working group is the Requirement Working Group, which I've been part of actively for 21 years as both chair and co-chair of the working group. Our purpose is to advance practices in education and theory of needs and requirements, definition and managing, and the relationship of needs and requirements to other system engineering functions. We want to expand and promote the body of knowledge and needs and requirements and their benefits within the overall system engineering community. And this is a list of different areas that we focus on as part of this. The leadership right now, the current chair is Tammy Katz in Ball Aerospace, myself, Rick Zini, and Mike Ryan. There's a link here. You can go to our website. If you're an Incosi member, Once you log into NCOSI, you can go to the Connect site and scroll down and find under the working groups, click on requirements, and all of the products and projects that we're working on you'll find at this Connect website. We have members from industry and academia, all with a common purpose of improving the practice of system engineering through the improvement in needs and requirements definition and management. And all the working groups focus on a specific area of interest, and you can become members of multiple working groups if you want to. And your involvement can be whatever you have time for and your interest. So becoming involved in the requirement working group, like I said, we're a large working group. We're very active with virtual events. We try to do every month when we have the time to have certain topics and stuff. And in the virtual environment, we send out notices to this. Then we have Zoom sessions where people can have discussions. Joining the working group allows you to be involved in what we're doing, either actively or passively in that respect. So in joining the requirement working group, when you log into the main NCOSI page and you go to your profile page, in the lower left of the screen will be what I show is number 1. And you have a thing where you can browse and join working groups. You click on that link and you'll get a link of all the committees and working groups that are in NCOSI, and you can scroll down to where it says requirements. And then when you go across to the right, you'll see the number of members, and then there's a button that says view. You click on that view button, and then you'll be taken into a list of all the members, current members of the requirement working group. On the bottom of that screen, scroll down to the bottom, you'll have the opportunity then to click on join this committee. And then that will make you a member of the working group. And one of the advantages of doing this is it allows us to communicate with you, sending out emails. We go to this location so we can send emails to all the membership. But you only receive the emails if you go to edit your information on your profile page, and under communication preferences, you need to opt in to allow working group emails to be sent to you. We have several release products that are very popular. The Guide for Writing Requirements. It's been translated into multiple languages. It's been revised several times. The most latest is the 2019 version, and we'll be probably putting out another version next year based on some of the current work we're doing. Another product that we put out is the Integrated Data as a Foundation of System Engineering. The focus of this is on practicing system engineering from a data-centric perspective, and you can download that. Products and work, we have the Needs and Requirements Lifecycle Manual. It's quite a detailed manual, over 400 pages, that goes into a lot of detail on developing needs and requirements, verifying, validating the needs and requirements, doing system verification, validation, and a lot of different information that you don't normally see in textbooks or in other guides and so on. So a lot of guidance, advice is in that. And then a pared down version of that for the needs and requirements, as we're developing a guide to needs and requirements. So it's more of a summary of what's in the Needs and Requirements Lifecycle Manual. And we're also doing a guide to verification and validation. That's a summary of what's in the manual also. So the underlying theory and concepts are in the manual, and then more of a practical step-by-step how-to are in the guides. And this is how all the products are related to each other. So the Needs and Requirements Lifecycle Manual is an elaboration of the System Engineering Handbook and what's in the CBOC. And then the guides then are developed to be consistent with what's in the manual. The white paper, Integrated Data Foundation System Engineering, from the data-centric perspective is kind of underlying all the products that we're developing. We do have a YouTube channel. You do a search for Nkosi RWG, and we have an introductory video that Tammy put out that you can listen to a little bit more about the requirement working group. That integrated data is the foundation of system engineering. This is a link to that a presentation I gave on that. It's more on not just the contents of what's in it, but how to use that so organizations can move more toward a data-centric practice of system engineering. The needs and requirements lifecycle manual, which a lot of the concepts I'm talking about today are being implemented. We did a lot of work during Nkosi International Workshop at the end of January, and the videos of some of the work we did is there, so you can get overview and contents of the manual, and then another separation on basic underlying concepts that's being implemented within the manual. It's to keep track of all of what we're doing and all the new stuff we add to. Advise that you subscribe. Once you get to this page on YouTube, hit the subscribe button, and then you'll be notified of any new presentations we put. So the focus of this presentation now is today's increasingly complex software-centric systems and how we address needs and requirements associated with that. You can see our systems today are very complex. I define complexity and not only the number of systems and system elements that make up a system of interest, but the large number of interactions within that system, and also the interactions of our system of interest with the operating environment and systems that are external to the system of interest. Yesterday's electrical mechanical systems had fewer interactions, both internally and externally. Those interfaces you could show in a drawing. You could have a mechanical drawing showing how things are bolted together, a wiring diagram, a piping diagram, a diagram of a connector and pin assignments. But that's not really easy to do when you're talking about interactions, when a lot of the interactions are between software components. So for software-centric systems, interactions, both internally and externally, in today's systems, they've increased exponentially, and as has the threats and vulnerabilities because of all those interactions, especially with the external systems. But in these systems, the critical functions are really carried out by the software, and the electrical mechanical parts that make up the architecture are really enablers for the software. So the focus tends to be a lot on, from modeling standpoint and everything, on the functionality and performance and interactions of the software. Nkosi's Vision 2025, first presented in Nkosi 2014, said a constant throughout the evolution of systems engineering is the ever-increasingly complex of systems, which can be observed in terms of the number of system functions, components, interfaces, and their non-linear interactions and emergent properties. And that's really typical of a lot of today's systems. Even my toothbrush, has all kinds of software, embedded in the toothbrush. So one of the things that just came out last week was this article about how software is eating the car. And it really illustrates a lot of the complexity that I'm talking about, a lot of the issues that we have, the challenges. Today, the success of a car depends largely on the software more than the mechanical hardware side. High-end cars may have over 150 electrical control units or more. Each one has software. The Ford's F-150 has greater than 150 million lines of code. 40% of the cost of a new car can be attributed to the semiconductor-based electronic systems, a cost doubling since 2007, and this will approach 50% of the cost by 2030. Each new car today has over $600 worth of semiconductors, consisting of up to 3,000 chips of all types. And so when you read in the paper now about chip shortages, and some um, automobiles and trucks that cannot be produced anymore because they don't have the chips. This kind of tells you why. 40% or more of a vehicle's development budget from the start of the development to the beginning of production can be attributed to systems integration, testing, verification, validation of the components and associated software. The network's harness attached thousands of components may contain more than 1,500 wires and over 5,000 meters in length and weigh in excess of 68 kilograms. So this really talks about the complexity. But one thing that really is disturbing is that nearly all the engineering control units design and software is outsourced to suppliers, with the OEM integrating these to create the integrated system with the desired customizable functionality. So approximately, but only 10% of the software is developed in-house. The other 90% is provided by as many as 50 or more suppliers, each having their own development approach, operating systems, languages, adding another level of complication, especially when performing systems integration, system verification, system validation. So individual suppliers often don't have insight into how their parts are going to be integrated, and the OEM really doesn't have a whole lot of insight into the internal workings of these ECUs either, which are procured more as a black box for a specific purpose. So this really, is an integration nightmare for these systems. When asked how difficult it was to know when a code change in one ECU affects another, you can see the results weren't very promising. So again, this is the integration nightmare. And every time there's an increase in functionality or a new feature that's being added to an automobile or a truck, that implies additional sensors, actuators, control units in the company's software, and extra system integration, verification, validation efforts to ensure they worked correctly when integrated into the system. Nearly 30% of defects that are found today are related to software integration issues, and interfaces interaction between the software components. And many of the recalls are due to a software issue today. And even when there's a hardware issue, they're increasingly coming up with a software fix to address the hardware issue. So this all illustrates, the issues that we have, the challenges in developing today's more complex software-centric systems. So the challenges that we have in managing needs and requirements across the life cycle is increasingly challenging when developing today's complex software systems, especially when they're being contracted out to suppliers. These challenges result in an increase in complexity, like I was just talking about, the role software has in the system architecture. The software-centric systems are more the norm. And then dependencies, the number of interaction between parts of the systems. And one of the problems in this dependency is the concept of cascading failures. You can have a failure in the sensor, and that could propagate through and cause other software systems and components to fail, and the whole system to fail because of these dependencies. And it's really hard to keep track of all this complexity without using models. There's just too much for people to keep track in their heads anymore. So that's one of the big reasons why we have model-based system engineering, is to deal with this complexity. And then the interaction between the system, the macro system as part, all those external interfaces are really an issue, especially the number of threats across interface boundaries and vulnerabilities to those threats. We've heard in the news all the issues with ransomware and cyber attacks, and that's become a top political issue that needs to be addressed. And so system engineers, we're going to be called upon to address these issues. The dependencies between project management and system engineering, we really shouldn't view the two as separate disciplines. They're highly dependent, and so we need to have ways to provide an integrated approach between project management and system engineering. And then the different life cycles process areas within the system engineering. In 15288, the COSI System Engineering Handbook, They define the different technical processes and the management processes separately because they have to describe each one, but they're not meant to be practiced in a silo or serially. They're meant to be practiced concurrently. We have increased oversight, more expensive systems, complex systems, safety critical systems, security issues, all this oversight, plus the internet, social media, puts more pressure on our systems. Increased competition that we have in consumer products, but also competition between, the different nation militaries is an issue. And this drives the pressure and need to reduce development time and time to market. We have a lot of risk that are inherent in developing these complex systems, both from a project management standpoint, a development perspective, manufacturing, system integration, verification, validation, operational risk. And we need to do these assessment of these risks up front, find a way to mitigate those within our systems design and address those. And because of all these challenges, it's surprising the number of projects that are over budget and experiencing schedule slippage. So John Malden, he's not an engineer, he's a investment counselor. And he had an article recently called Technology Rules. And he observed that it's remarkable how many industries and government agencies are still operating on ancient technology and just muddling through. And of course, he doesn't recommend people investing in those companies. He says, what happens when those organizations take off their old tech handcuffs? Well, they're going to run into they will run better and develop new capabilities that they never had before. Customers, workers, and investors will benefit. And humans have a comparative advantage at higher levels of distraction, creativity, intuition, and holistic judgments. Each is necessary. So the best technology does not automate complex problems, as many assume. They equip people to solve them faster and more effectively. And so that's what NCOSE is trying to do. With this system engineering, you can think of system engineering as a technology, and that technology is evolving, and we're in a model-based world now because of the complexity, and so we need to evolve our technology and practicing system engineering. We're 21 years in the 21st century, so why are so many still practicing system engineering based on outdated 20th century electromechanical document-centric methodologies? So to address these challenges, we need to change how we currently practice system engineering and project management. And I say how we practice, if you look closely into what is in the NCOSE System Engineering Handbook, all is there that's needed. It's surprising how many organizations really don't follow what's in there. If they did, they could address a lot of these challenges already. So key areas of change discussed in this presentation is the concept of needs and requirements, integrated multidiscipline collaborative project teams, minimizing silos, manage the integrated system from the beginning, allocation and budgeting for software-centric systems, data-centric practice of system engineering, increased focus and validation across the lifecycle. So that's what I'm going to focus on for the rest of the presentation. So first of all, needs and requirements. First, we'll talk about needs versus requirements. So when we talk about needs, we're talking about a perspective that represents the stakeholder, customer, acquirer, or view of a system of interest. How do they view the system? As some people call it, as a black box. What do the stakeholders need the system to do that will result in their problem be solved or opportunity to be realized within defined constraints? And so the needs communicate these expectations for the end state once the system of interest is delivered. In the end, what will make a customer happy? I don't know how many of you read the book, Highly Effective Practices, and the last one of the practices is keep the end in mind. And that's what system engineers always want to do, is keep the end in mind. And the end is what will make our customers happy. So by defining a set of needs, we will validate then our system of interest against the integrated set of needs to ensure that what we deliver will make the customer happy. Now, the requirements, on the other hand, represent the technical developer view of the system of interest. What must the system of interest do in order to meet those needs? And so it's a different perspective. It's the system engineer's perspective. Okay, the stakeholders have needs. What do we need to do in order to meet those needs? And a system of interest will be verified against the design input requirements. And so the quality of the requirements is dependent on the quality of the needs from which they are transformed. And so the approach that we're talking about is that you define the needs first, and from those needs, you'll transform those into the set of design input requirements. So the needs and requirements are the common threads that tie all the system engineering lifecycle activities and artifacts together. And from a holistic view of system engineering, needs and requirements must be defined and managed in the context of all other SE process areas rather than a silo. So rather than just focusing on the needs and requirements, we need to focus on both needs and requirements. One thing I really don't like anymore is hearing the term requirements engineering, because it tends to put requirements in a silo, and it doesn't recognize the fact that it's really needs and requirements. We were talking about maybe changing the requirements working group to be the needs and requirements working group to have that emphasis on both needs and requirements. Now, we talk about needs before requirements. There's a lot of work that's done before we can write the requirements. So we start with stakeholders. They identify the problem, opportunity, the reason for the project. They define a set of mission goals and objectives, measures of suitability. The stakeholders have needs, requirements, and expectations they expect to be addressed by the system that we're developing. There's always going to be a set of risks that we need to address, regulations and standards that constrain what we're doing. We have to be compliant with those regulations and standards. We have higher level needs that were allocated to our system that we have to address, higher level lifecycle concepts, higher level requirements. All of these are constraints to what we're doing. Existing systems and developing systems really that are in the macro system we're part, we have to interact with. They're going to constrain our system. Cost and schedule are always issues. And then a lot of what we're doing, we're pushing beyond state of the art. We're using new technologies. And so just technology itself is a constraint to what we're able to do. And so all this information feeds into what I call lifecycle concepts analysis and maturation. So we collect all this data through elicitation activities and other activities. We develop a preliminary set of lifecycle concepts, and then we go through an analysis and maturation. It's from that system analysis that we then transform those into an integrated set of needs. So like I said, there's a lot of work to be done before defining the requirements. And what we want to do is establish the completeness, consistency, correctness, and feasibility before defining needs and transforming those into the design input requirements. The one product I talked about earlier, the Guide for Writing Requirements, it lists a bunch of characteristics of well-formed needs and requirements. And one of the characteristics are the completeness, consistency, correctness, and feasibility. Feasibility is interesting in that feasibility really exists in the physical world, not a conceptual model world. And so as part of this, we're going to have to dive down into the physical architecture and design to assess what our critical technologies are, assess what the maturity is, and have a plan for maturing those technologies so that can be used within our system. To baseline a set of needs and set of requirements that we haven't done this assessment, then there's always an issue whether we can even meet those requirements if we don't have the right technology. So the lifecycle concepts and maturation piece that we have, that work is done using the concept of refinement. So we have a preliminary set of lifecycle concepts that we define. We go in and develop our models, do analysis and maturation of those models to the point that we can we have a functional architecture we can map to possible physical architectures, and this establishes a trade space. And then we can take and do a feasibility analysis of each of the candidate architectures, assess the technologies, the risk through our trade studies, and we zero in on initial physical architecture and corresponding set of lifecycle concepts. And these section numbers that are showing here are sections within needs and requirements lifecycle manual that goes into detail on each of these. Then we increase the resolution, and we may have to go through several cycles, but once we have at least one set of feasible lifecycle concepts, we can develop an integrated set of system needs, preliminary physical architecture models, plans, budgets, schedules. When I talked about the set of lifecycle concepts, I'm not talking about just operations. I'm talking about the whole life cycle. So what's our concept for development? What's our concept for acquisition? What's our concept for how we're going to manage the system? What's our concept for how we're going to do design? What's our concept for how we're going to do integration? For system validation, our concept for system validation, manufacturing, transportation, storage, actual operations, but maintenance, and then retiring the system. All of these different life cycles could be a source of requirements that must be addressed. So we want to develop the set of life cycle concepts and not just focus on just operations from that respect. So out of all this, we have a lot of information that goes into defining our integrated set of needs. Remember, the integrated set of needs are the perspective of the stakeholders, what they need the system to do, and then those are going to be transformed into the design input requirements that communicate what the system must do to meet those needs. So we must understand the stakeholder needs before the system of interest, before defining what it must be to do those needs. So in the end, rather than just ending up with a set of design input requirements, we have a set of requirements along with an underlying analysis and integrated set of needs from which they were transformed. And it's an underlying analysis that's really important. A lot of people, when they talk about writing requirements, focus on how you write the requirement statements and thinking if you write requirement statements properly, you're going to have a good set of requirements. And I found that's maybe 20%. I think it's that underlying analysis that we do is really what makes you have a good set of requirements. And then how you write those requirements is just communicating the results of that analysis to the design team. And when I talk about design input requirements, I'm talking about the requirements that are inputs into the architecture and design processes versus the outputs of those processes, which I refer to design output specifications. The next topic is the integrated collaborative multidiscipline project team. And so too often organizations are set up where the project management team and the system engineering teams are separate from each other. They may not even be located together, and that can be a problem. So the approach that we are pushing is that we have a core team made up of both project management and system engineering top managers. They're supported by a project management integration working group and a system engineering and integration working group. And the integration part is really important because we're managing the system as an integrated system from the beginning of the project. Then they're supported by subject matter experts in the different disciplines, and they're supported by lifecycle stage support personnel. So in this context, project management and system engineering are the two sides of the same coin. And the team is made up of both project management and system engineering personnel and are tightly dependent. So all these different discipline experts work together in an integrated multidiscipline collaborative project team. And this can be challenging when outsourcing development to a supplier. So the integrating organization needs to figure out how are we going to be able to include the suppliers and manage the system development in an integrated fashion. And you can see from the automobile example I gave earlier, this could be really challenging, but not doing this is going to drive up the cost tremendously when you start integrating all the pieces together, and could take a lot of time and money and cause a lot of rework. So to prevent that, we need to be thinking a little bit differently in how we manage our suppliers. And so when you look at the system engineering V and you look at the different processes up here at the top, you notice that concurrent definition analysis maturation is applied iteratively and recursively as we move down the SEV. These are not serial processes. So we're doing all these concurrently with that multidiscipline team. And all of these are highly dependent and interrelated. So each of the experts will focus on their area, but there needs to be a common data repository for all the data information being generated in this respect. And this is a lot faster and cheaper for product development than the classical waterfall serial document-centric processes many practice today in a siloed fashion. And by doing this concurrently, it aids in establishing correctness, completeness, and consistency of all of our artifacts. And I've been talking about managing the integrated system from the beginning. And so you notice in this chart, system integration is shown across the whole life cycle in developing the system. And so it should not be thought of as just occurring on the right side of the V when you're putting the parts together, but we need to be considering the integrated system from the beginning. And this is especially true in models. You can't take a separate models and add them together. If I have a pendulum and I develop a model for how the pendulum works, and then I want a new system that includes two pendulums, I can't take the two models and add them together because I have a different system. If I have an automobile and I model it, and I have a trailer and I model it, I can't add those together, the models together, because together they're a different system. And remember, the behavior of a system is a function of the interaction of the parts. And so we have to find a way to develop an integrated model from the beginning. The integrated system of interest must be managed from the beginning, like you said. And again, the customer-supply relationship must allow this to happen. And so, we have system engineering, there's a hierarchical view, and the focus is on decomposition because it makes it easier to develop our system of interest in bite-sized chunks across multiple organizational units, internal and external, based on specialized knowledge and expertise. And this concept of decomposition is one of the great strengths of system engineering, but it's also one of its biggest issues. Because notice that in this view, the interactions between the parts is not shown. So that integrated piece is missing. And in doing this, the focus tends to be on the system elements that make up the system of interest rather than the integrated system of interest itself. And this leads to developing the individual system elements in silos rather than, and optimizing those pieces rather than optimization of the integrated system of interest. And so this is something that we need to address more when we're developing. And so we go back to the drawing I had earlier, is we take a holistic view of the integrated system of interest and understanding the system is greater than the sum of its parts. So we're going to focus on the behavior of emerging properties of the integrated system based on these interactions, as well as interactions between our system and external systems. And to optimize our system of interest, then, the system and system elements within the architecture may not be able to be optimized. In fact, some of them may have to be sub-optimized in order to meet, in order to optimize the overall integrated system. Here's an example, Boeing 787. They had over 30 companies based in countries around the world were building large portions of the airplane. To help manage this complex system, they developed an integrated model that had greater than 2,000 functions, greater than 5,000 data flows, greater than 1 million data parameters and 50 million objects, with an average of 3 relationships per object, as well as 1,000 geographically dispersed users involved in the modeling effort. And so, to manage complex systems, we need this integrated model. And then different suppliers can work in their piece of the model for their particular system of interest, or that they're responsible for, but it's all done in the context of the larger macro system in which their system is a part. And along with this goes then, the allocation and budgeting process. And what worked well for the electromechanical systems of yesterday don't work as well for our software-centric systems. So we need a different approach for doing that. And in this approach, the second layer now is different than before. Instead of the second layer being systems and subsystems, we have our system level set of requirements for a system of interest. And when we do the allocation and budgeting, and I'm talking about budgeting and performance and quality, as well as budgets for mass and cost and so on. In this case, I have hardware, mechanical, and software as the next level. And so I would look at a system level requirement and say, what role do these three have in meeting that requirement? And then every piece that has a role, we'd allocate them to them. And then they would sub-allocate to the parts of the architecture that make them up. Worked with several different medical device companies that mainly deal with instruments and do an analysis of biological samples. And they found that this approach worked really well. Only what they did is, under hardware, they combined the hardware and mechanical into an instrument on the left. In the middle, they had what they call an assay, which is the biological sample and chemistry, the reagents part of it. And then they had that would be put into the instrument. And then the instrument collects the data that is analyzed by the software. And that's the software that has the key intellectual property rights of the company. It's going to analyze the data from the instrument of those biological samples. And it's the software that's going to then make a determination of what they're trying to detect. And this really works well in those organizations. The different cultures between those developing the instrument and those developing the biological samples and those doing the software, really worked well. So this system level allocation and budgeting needs to be done very early. If you go back to this view, it may be down at level 4 before software even gets talked about. And that's really can be an issue, because in the software-centric systems, the critical functionality and performance are embedded in the software, and the hardware is the enabling systems. And because the cost of the development may be more in the software, and software is the critical path to the schedule, then we need to get requirements to the software as soon as possible. And this enables the software to be developed and managed as an integrated system. So you can have one data dictionary. So all the communication between 150 modules can be managed in one location, all the communication buses and so on. But it's very important to understand the difference between standalone software applications and embedded software. Embedded software is very dependent upon the hardware sensors, displays, actuators, processors, and so on. And so all the hardware are constraints to the software. So the software cannot be developed independently of the hardware systems in which they interact. So this is a little bit different approach to normal software development. Our data-centric practices is system engineering. I talked about the integrated data as a foundation of system engineering. The basic concept of this is in the blue boxes at the top. In today's world, a lot of people develop those in a document-centric world using separate applications that are developed in silos, resulting in inconsistent data and information. In the integrated data as a foundation of system engineering, we take this information, put it in an integrated federated shareable sets of data. And then on the bottom, each of these artifacts then are visualizations of the integrated federated shareable sets of data. And what we configuration manage, instead of the individual artifacts, we configuration manage the data from which they are represented. And so when we configuration manage a set of data, we're automatically configuration managing all the visualizations of the artifacts that are represented by that set of data. And so in the Needs and Lifecycle Manual, we talked about the information-based needs and requirement definition and management. So I talked about the needs definition. They're transformed into the set of requirements. But also from a modeling standpoint, we have functional models. We have our interface diagrams. In that we have requirement statements, attributes, our verification, system verification artifacts. We're mapping the functional architecture to physical architecture, which is transformed into the engineered system, validated by system validation artifacts, and so on. So this is kind of a different view. And to make this work, traceability is critical to document all these relationships. And again, this has to be done in a model environment. It can't be really done in a document-centric environment. So what we end up with is we have design inputs, which are part of the information needs requirements development management part, resulting in a set of design input requirements. And then those are transformed by the architectural design processes into a set of design output specifications, which then are transformed through manufacturing coding into the system of interest. That's all the design outputs. And so a lot of people that are practicing model-based system engineering are really practicing model-based design, where their process starts with a set of requirements. But as I've talked about it before, the requirements come from someplace. They come from the needs. And so by adding the two together really is the intent of model-based system engineering in that respect. The last topic is increased focus on validation across the life cycle. We talked about, we showed this before, and so I have system validation not just on the right side of the V, but system validation occurring continuously throughout the system life cycle. And in this case, then, our needs, we're going to validate the needs, communicate what they're supposed to. We're going to validate the design input requirements against the needs, validate our architecture, our design, the design output specifications, and the realized systems, element systems, and integrated system of interest. So we're doing validation across the life cycle to make sure that we're going to make our customer happy, like I talked about before. And by doing an increased system validation on the left side of the V, it's going to decrease the issues we find on the right side of the V, compressing our system integration, system validation time scale, reducing cost, and getting things to market quicker. And so when we talk about the needs themselves, they're going to be validated against the lifecycle concepts, what they were transformed from, as well as validated against all the information we collected from during the elicitation activities. They're also going to be verified against the rules for writing good sets of needs, and the lifecycle concept likewise would be verified against the rules for defining lifecycle concepts. These design input requirements then feed into, are transformed into the design input requirements, which are transformed into design output specifications and into the system of interest. So across the top, you see we're doing continuous system validation. The system of interest is validated against the needs. The design output specs are validated against the needs. Design input requirements are validated against those set of needs. From a verification standpoint, it's very important for both validation and verification that we don't use the terms generically, but we include the context. So you notice that I have system validation, design validation, requirements validation, production verification, system verification, requirements verification, design verification. So it's very clear what I'm verifying and then what I'm verifying against. in this respect. This drawing has become very popular, and it's going to be included in the update to the INCOSE System Engineering Handbook version 5 when it comes out in a couple of years. So that talks about, system validation, and we need to have an increased emphasis on system validation, not just system verification. So system validation is validating the realized physical integrated system of interest meets its intended purpose as defined by the set of needs, and identify and assess behavior and emerging properties. Remember, we said that a system is greater than the sum of its parts, and that the behavior of the system is the function of the interaction of the parts. And the emerging properties may occur both good and bad that weren't really reflected in the needs and requirements. So part of system validation is characterizing our system and assessing this behavior and the emerging properties. And we want to do this in the actual operational environment when operated by the actual intended users. And I said up at the top here, realize physical integrated system of interest. We can do verification validation activities on the design using models, but that only gives you a theoretical indication of behavior. It doesn't represent the actual physical behavior of the system. Now, what I've shown here is really the classical definition of system validation, but in today's complex world, increasing vulnerabilities, we need to add and does not enable unintended users to negatively impact the intended use of the system. So as system engineers, we always have to keep this in mind. Even if we didn't get needs and requirements from our customers, we still have an ethical obligation to address these risks. So system validation, what's more important? System verification and system validation. Really, project success is based on passing the system validation and making the customer happy. So we could pass system verification and fail system validation, and we have a failed project. I find a lot of contractors that their contract is to meet a set of requirements, and they say system validation is not my job. That's the customer's job. But I think that's kind of a narrow view of system engineering, because they should have been validating the requirements against the customer's needs. They should have been validating their design, make sure they write design against those needs, in doing their job. And so we have to ask, if validation is so important, what do we validate against? And the answer is the needs. Where are they defined? Who actually defines it? Who's responsible for defining it? And who's actually responsible for system validation? And what is actually necessary for acceptance? And all this needs to be defined clearly in all the customer supplier agreements, our statement of works, our supplier agreements, and so on in that respect. So I have some people that looked at this presentation, and they looked at all the work that's done before defining requirements and defining the needs, and they said, we really don't have the time and money to do that. We can't afford to define the set of needs. And I think that's is kind of a narrow view. There's a concept of technical debt, things that you need to do and you delay later. You're going to have to address later, but a lot more expensive. So when people tell me we can't afford to do the upfront work, I tell them you really can't afford not to. So that concludes the presentation. Sorry, took a little bit longer than planned. And so answers. Hello?
I was muted. Sorry.
Oh, okay.
All right. Thanks, Lou, for your presentation. I think was really a rich presentation with a lot of good information and good insights. Um, the material and the manuals and especially the first product that was released by the requirements working group is really useful for me in my daily job. I use a lot, and we use as a company as a reference for our work on writing requirements. And I'm looking forward to have the needs and requirements manuals and everything released to have this available for everyone and help us to identify better needs and manage better requirements. I think it was great, and the work done by the requirements working group is really good. And I participate in some of the meetings, and I enjoyed a lot. And I recommend everyone who are a member of Incosi and interested in requirements management and requirements needs and requirements definition to be part of it. Um, we have a couple of comments and questions here. I will start with them before I jump in with my comment. We have one comment or one question from Luciano. I'll put on the screen now. He's asking, is planned obsolescence a strategy for automobile software development? You have any thoughts on that?
Um, Well, one of the biggest issues I had in the software development part, I worked with, I taught some classes for a major automobile supplier. And two issues I found is one is that they weren't really, a lot of the people developing the software, they were developing algorithms and requirements for the software. It was going to be outsourced, but their education was from a software side of developing standalone applications, and the software people really didn't have a good understanding of systems engineering and the dependencies the software has in the hardware, and then the dependencies, the interactions of all the different software pieces, that they shouldn't be developed in a silo. They need to be considered as an integrated system. And that brought into a problem, and that when I asked before the class, I said, could I see an architecture of the automobile and how all the parts interrelate, especially the software? They said they didn't have that. It didn't exist in the organization, which I felt kind of hard to believe, but that was really a big challenge.
All right. Yeah, and we have another comment and question from Frederico, saying, if the customer has a very comprehensive need, the SE must translate or indicate which requirement must be met to cover that need. However, what would be the main steps for us to translate it? Any thoughts on that?
Yeah, so the first thing is that you understand what the needs are, and then did the customer have any underlying analysis from which they defined their needs? Did they develop models or anything, or did the needs just, it was an exercise in writing and they just wrote down a bunch of stuff without that analysis? And so from a supplier standpoint, that puts you, if the customer gives you the set of needs plus the underlying analysis which they came from, then you can take that information and you can enhance, you can elaborate on the models, and you can then change perspectives and ask yourself, in order to meet that need statement, what is the system going to have to do that? And then the result should be necessary and sufficient set of requirements to meet each of the needs. But without the underlying analysis that goes with that, it's going to be very hard to do that, because one of the sayings I have is writing requirements is not an exercise in writing, it's an exercise in engineering. And for these complex systems, you know, using the models and diagrams to help see what's going on is going to be critical in order to be able to develop a good set of design input requirements that will result in the needs being met.
Yeah, and I have an experience with that, because I used to work for both sides. I used to work for the client side, defining the needs in order to acquire a system to be used, and also in the supplier side, and from my experience, both sides is critical if the client or the acquirer, if it's not a developer, to have a proper systems engineering skills in order to understand really the problem and define better the needs, in order to give those needs, or to forward those needs to the supplier. This makes the life much easier for the supplier to understand what really the problem is, and also for the client to have the problem really solved at the end of the day. So yeah, I don't know if you have any thoughts on that, on the importance of kind of SE skill in the side of the client, or the one who is acquiring the system but not developing the system.
Yeah, the customer has to be an informed buyer. They can't just blankly throw out stuff. If I throw out a set of needs or a set of requirements that are incomplete, inconsistent, actually not even correct, and I haven't even addressed feasibility, what's the supplier supposed to do with that poorly formed set of needs or requirements? And if the needs don't have the underlying analysis to address correctness, consistency, completeness, and feasibility, then any requirements you develop based on those needs will have those same defects. And so you're really the customer's really setting the supplier up for failure if the customer hasn't done that upfront work. So in today's world, the customer has to have some degree of system engineering capability so that they can develop well-formed sets of needs or requirements, or both.
Yeah, totally agree. And sometimes the client gives a set of requirements to the customer, and defining already the type of solution, which is not really the case at sometimes it is, but some others are not. It's just preference from the client, and this needs to be really clear for the ones who are developing the client side, right?
And that's why in what we're doing, we're talking about, instead of just saying requirements, we're talking about design input requirements to make sure people understand we're trying to define the what that's going to be an input to the architectural design process. And then the outputs of those processes, then we call design output specifications. So we make a clear distinction between the two, so we don't mix them.
Yeah, that's true. I think we have we have two more if you have time. Can you go ahead with two more, Lou? Are you okay with that?
I'll stay here all night. I'll stay here all night if you want me to.
Okay. Yeah, we have couple of questions. We have another one from Luciano asking, do you think that ethical verification can be implemented in SE? Example of Void, Volkswagen software that overcome emission control.
That all goes on the culture of the organization. Multiple problems have existed in the past by different organizations that, the budget was the all-encompassing. Chrysler had a problem several years ago where one of the suppliers gave them a ignition switch. It did not meet the requirements, but from a scheduled pressure standpoint, they used that defective ignition system, and the result is that if people had a heavy keychain and they hit a bump on the highway going 70 miles an hour, it could cause the ignition to go out of run, and then the car lost brakes steering, and people got killed. And you saw the same thing in the Boeing Max. It traced back to some of those issues. Volkswagen had that issue. But that really goes into an ethics, culture thing of the company. I really think that when you define feasibility, in addition to cost, schedule, and technology, you should add the word ethical.
Yeah, that's right. And yeah, we have. Yep. Go ahead.
I saw another question here about, do you have a reference of publication
Yeah.
where allocation budgeting,
Yeah.
the software-centric systems concept is discussed in more detail? And I go into that in a lot more detail in the needs and requirements lifecycle manual. And for those of you that are members of NCOSE and join the requirement working group, you can go to the requirement working group Connect page and go under the needs and requirements lifecycle manual, and you'll see a draft of that document now. Our plan is for the manual and the guides by the end of June to be able to be submitted to TechOps, and then TechOps will have an approval process that will probably take a month or so. And so hopefully in the fall, all three of the products, the new products, will be available in the store, in NCOSE store, and hopefully it'll be free.
Yeah, okay. Yeah, that was great. So I shared already the link for a place where I uploaded the slide deck. So it is in the LinkedIn event that we created. So I just attached it there in the chat box or messages at LinkedIn. So you can check there and download. It was a really good discussion, Lou, and I would like to thank you again for your time, and then thanks everyone for attending and to be here at this time. I hope we can have other events like this, and talking about the release of the needs and requirements manual and everything. So if you want to just to say your last words for today, and feel free.
Okay, well, again, thank you for having me. My email address is on the front of the presentation, wheatlandconsulting.gmail.com. So if anyone has any specific questions or would like some help in something, feel free to send me an email, and I'll be happy to help.
All right. So thanks a lot, Lou. Thanks everyone. So we're gonna have as usual another presentation in July and so on. So you're trying to keep one presentation per month. And just stay tuned to our social media. We're gonna update from there. And I hope you see you again in the next events. So thanks a lot, Lou. Thanks everyone, and have a good evening.
One last comment. This is a very popular topic, and if anyone that was here has any friends or coworkers would like to listen to this, I'm giving the same presentation tomorrow morning, 10 o'clock Central Daylight Time here in the U.S. For the monthly NCOSE webinar. So if people have anyone else that they want to listen to this in real time, they can attend the presentation tomorrow morning.
Yeah, and this one will be available on YouTube, on our YouTube channel, as usual. So if you want to check later, we'll be there. All right. Thanks again. Thanks, Lou. Thanks everyone. See you next time.
Bye-bye.
All right.